Hello, students. We went through one example really fast, and I want to go through it again and show you some variations. Not so much an example, but we went through that whole differentiation thing a little quick. So I want to do that again. So we have the binomial theorem, which tells us that this is equal to x plus y to the n. And then we have the ability to plug in any y we want. So let's try to simplify things, and let's plug in, kind of probably don't want to plug in 0 for y, right? Because then most of these terms are 0. So what's the next most simple thing that we could plug in? Just like without knowing what we're going to get, you're going to want to plug in 1. So okay, we get this simplified version of the binomial theorem. And then what we did then was differentiate both sides with respect to x. So we would get this and choose x to the I minus 1 is equal to n times x plus 1 to the n minus 1 times the derivative of x plus 1, which is just 1. Okay, now one thing I did really quick is I said, hey, if you plug in minus 1, you'll get a 0 on the right. Here you'll get these alternating positive and negative signs, and you get this nice identity, which can be explained in a very nice way as a counting problem once we get to inclusion-exclusion. But we're not doing that now. We're doing something else. So I want to introduce another identity we can get out of here, and that's if we plug in 1 for x. So in minus 1, might as well plug in 1. Once again, let's avoid zeros. So 1 is the logical choice. So here we get n times, I don't need a parentheses because I can just write that as 2 to the n minus 1. So very nice identity, but we're just sort of staring at symbols on a paper. It might not have a whole lot of meaning for us. So let's try to think about what this would mean, and maybe we could prove it in a different way. So let's think about this thing on the right. So I have 2 to the n minus 1. Now we know that 2 to the n is the number of subsets of size n. So this here is the number of subsets of size n minus 1. Okay, and this is just the number of ways we could choose one thing out of n things, or sort of n choose 1. Okay, so let's try to think about a situation where you'd have one thing to choose. You have n possibilities. I mean, let's say we have n things or n people. And this would be the way we could choose one particular thing and then a subset from the remaining ones. Okay? Because if I take one thing out, now I only have n minus 1 left. How many different subsets are left? Well, 2 to the n minus 1. So what this would tell us is this product, by the product rule, this right-hand side is the number of ways wrote the S too fast. I wanted to get through that word. Number of ways to pick a leader and a disjoint from the leader, I mean, disjoint subset of followers. Okay? Because once we've picked the leader's gone, there's n minus 1 people left, and I should say from n people. So these are the number of ways we could make that decision. So maybe I could count this left-hand side, or I could count this in a different way and make that equal to the left-hand side. So what's another way that I could count this? Well, instead of picking the leader first and then picking the subset, what if we chose an entire subset, we remove them from the group, and we pick one of the people from that subset to be the leader and separate them from that subset? So let's see that would count the same thing, right? Because either I have a subset of size 0, well, let's not do 0. Let's say either I have a subset of size 1 and then I pick the leader and then the subset becomes empty. Or I have a subset of size 2 and then I pick the leader and the subset becomes size 1, and so on. So let's count each of those possibilities. So how could we do that? So what I want to count is the number of ways to pick a group, of size I greater than or equal to 1, because we must contain at least one person because we're going to pick a leader, right? And then take a leader, from that group. Okay, so number of ways we could pick a group of size I greater than 1 and then take a leader from that group. Well, we have n different people, so either we could take a group of size 1 and then take one person, the only one choice I have, to be the leader of nobody, or then I could take a group of size 2 and then from the 2 people I have to choose one of the 2, so 2 choices. Okay, or I could take a group of size 3 and then I'd get 3 choices, or I could take a group of size n and then get n choices. So I put this together, and what does that equal? Well, we get the sum from I equals 0 to n of, no, not I equals 1 to n. Sorry, I'm jumping, not yet. I equals 1 to n of n choose I times I. So you say, hey, wait a second. This is very similar to what I have here, but there's one change. This one starts at 1 and this one starts at 0. Yeah, but look at the 0 term here. It's not really there, right? Because this is just 0, because it's multiplied by 0. So these two are the same, okay? So we proved this identity by taking the binomial theorem, plugging in 1 for y, differentiating, and then plugging in a number for x, and it was valid. We got this identity, and it was great. But we could also look at the right-hand side as a counting problem. And then any other way that we can count the same thing, we can actually use our rules like the sum rule and the product rule. That's all we used here, sum and product, right? We used the fact that each of these situations was disjoint, and we used a product rule in each of those situations. So we use that in order to count this same thing in a different way. And if you count the same thing in 2 different ways, well, the 2 sides have to be the same because you're counting the same thing. So what we proved was this. No reason to write it again. We proved this again, but by visualizing it as a counting problem and then counting the same thing in different ways. And this is very useful. Sometimes the proofs can be very messy of certain things if you just try to do things sort of algebraically with algebraic manipulation, but there's a very short proof if you just think about it in a certain way. And you'll see that's coming up. There's a proof with multinomial coefficients that has a few different ways to do it, and one of them is very messy, so messy I'm not even going to show you because I don't like the playing with the indices is not pretty, but beautiful short counting argument. So always try to think about that. If you see an identity like this, think maybe I'm counting the same thing in 2 ways, and then try to do it like that, or give it a shot.